Okay, good morning, everyone. Today, Alex and I will be introducing our project called Solar. And yeah, so here's a rough roadmap of the contents which we'll be covering today. We'll start by going through an introduction to Solar. Then we'll go through the design of our language, as well as the architecture and implementation. And then finally, we'll do a live demo of our online interpreter and talk a little bit about the future of Solar. So the language we worked on for this project is called Solar. Solar is our variant of the Lua programming language. And although it is similar to Lua, it's not exactly a carbon copy of Lua. And we decided to name it Solar because we were inspired by Lua's name, which meant the moon in Portuguese. And Solar means the sun in Latin. So we decided to work on Lua because we felt that scripting languages were often underlooked because they are often interpreted rather than compiled. Yet we say that scripting languages still had some value in a variety of applications. And amongst the other scripting languages, we were interested in Lua because Lua uses a free-form syntax where whitespace and indentation can be freely inserted. Furthermore, Lua does not strictly require the use of semicolons, and Lua also has a very simple syntax to learn. So this is why we've decided not to implement a carbon copy of Lua, but rather add some of our own adaptations to the language. So our approach to designing the language Solar was to use Lua's syntax as the base and also adapt ideas from other more mainstream languages, such as Java, JavaScript, and Python. And then we incorporated our own design decisions. Now here's a rough outline of what we've managed to achieve so far. So basic things like comments and essential language constructs such as basic data types like numbers, booleans, and strings, arrays and tables, conditionals, loops, functions, as well as printing output to the console have been implemented already. Also, we implemented some form of runtime type checking, and we've also implemented support for optimizing certain tail recursive functions. A standard library and a browser-based programming environment has also been deployed. And now Alex will go through the design of our language.
Thank you, Yu Heem. So let me share about the language itself. Of course, due to time constraint, we won't be showcasing the entire language, but rather we would like to highlight some of the differences between Solar and Lua. So, the first example I will share is string concatenation. So Lua uses two periods as string concatenation, and we decided to change that to the plus operator because we see benefit in familiarity. And of course, we mentioned that we implemented certain standard libraries, such as the string library, which has the popular string APIs as indicated here. So for variable declaration and assignment, this is an important one because in Lua, there is no let keyword. All variables by default are global variables. So we do not like that design, and we created a keyword called let for explicit declaration. So with declaration and assignment, of course, the important issue is scoping. So we decided to use the standard scoping rules that we see in JS, C, and Java. So for arrays, the difference is not big. We just wanted to tweak it a little bit. Lua arrays starts from index 1. Of course, we see the benefit in familiarity, so we chose to use 0 index. And as mentioned, we also implemented array library in the big standard library. So for printing, printing is pretty much standard. We just gave Solar programmers a little bit more of quality of life because we understand that sometimes programmers want to print out containers such as arrays. So Lua does not have a built-in way to do so. It prints out a hexadecimal ID unique to the container, and honestly, that doesn't mean much. So we display the entire container in Solar. Now for conditionals, these are if, else if, and else blocks that you would expect in C family languages. I just want to point out that these are not conditional expressions, which you see in source, for example. So you can just write a couple of if blocks without an else, for example. Yep. Now for loops, if we look at this sample program on the left, it will loop from 2 to 10 in Lua. We changed it to 2 to 9. So once again, you see our repeating kind of ideology of having familiarity in language. So we look from 2 to 9. We do not include the last index. Now, for looping through a container, like an array. So we believe that looping through an array in a for x in array kind of syntax is very popular and very mainstream. So we decided to provide that kind of syntactic sugar to programmers. Lua does not have this convenient syntax for some weird reason, so we implemented it. Okay, so now let's talk about functions. So we'll be spending a little bit of time here. So if we look at this sample program, this is a typical way you would declare a function in Lua and in Solar. So it's the same for function declaration, but the philosophy, the underlying philosophy is different. So let me share on the next slide. So Lua's philosophy on functions. So this is Lua, not Solar. Functions can be declared anywhere, globally or in any block, like even if it's inside a function. And the function body can utilize values declared outside the function. So this is Lua. Now, we do not agree with that, right? We have our own philosophy of the functions. We believe that functions should be a generic utility that only depends on its input. And that means that functions that we write ourselves should behave like standard library functions. So in our implementation of function declaration, we restrict function declaration to the global scope. You can only declare functions in the global scope. And your function body can only depend on your parameters. The function body will not be able to understand any global variables. So that is our philosophy, and we implemented that. Yep. So even more on functions, right? All functions are passed by value. And I'm very happy to share that Solar supports tail recursion. So execution of tail recursive functions would not blow the stack, because tail recursion, as we know, consumes a constant stack space. So this will be showcased in the live demo by Yu Heem later, so keep a lookout. Yeah, so let me share the architecture and implementation of the project. So this diagram is a high-level overview of the software architecture. What we essentially implemented is an interpreter. So it takes in a Solar program and outputs evaluation result. So within this interpreter, there are three important components from left to right, of course. So the first component is a parser. So instead of using a parser generator like Antler, we chose to use an open source Lua parser because Solar is heavily inspired by Lua. So we decided to use a Lua parser. And the second component is a very, very tiny component that was handwritten by us. It's the semantic analyzer. So it's just a very tiny component to conduct another layer of check before we evaluate the program. And of course, the heart of the interpreter is the evaluator. And of course, this is handwritten and it's our main work for the project. So let's talk about the evaluator itself. So the evaluator we built is what we know as a tree walk interpreter. The design is very similar to the meta-circular evaluators seen in SICP and SICP-JS. So of course, the general strategy is to recursively evaluate the abstract syntax tree. It is also important to note that runtime type checking is also performed within the evaluator module. Yep. So I mentioned earlier that we support standard scoping rules, right? So the high-level idea behind how we implement scope is we decided to implement scope as a TypeScript class. Every scope will have its own symbol table and also a link to its parent scope. So of course, the global scope will not have any parent. I will show a sneak peek of the actual code implementation in the next slide. So as mentioned, a scope is a TypeScript class in our project, and it has two members, a symbol table and a parent scope. So when it's first instantiated, the symbol table will be, of course, initialized to an empty one. And the parent scope will be determined by the constructor argument. And we also added a few useful APIs in the class. If we want to do a symbol lookup, we will call the lookup function. The actual implementation I will not share here. And if we want to do a variable assignment, we can call a assign function, which takes in a symbol and a value. And so, of course, this assign function would modify one particular symbol table. Yep. So I'll hand the time over to Yu Heem. We'll talk about how we implemented the. We'll talk about our browser-based programming environment. Yeah.
So for our browser-based programming environment, we've deployed it using Netlify. So you can access it through a link. And the text editor we are using is similar to the one used in Source, which is the ACE editor, which is an embeddable code editor written in JavaScript. So users can write and execute programs on our website and run them through this online interpreter. So program output will be displayed on the output console. So I'll now go through a live demo of the website.
Yu Heem, I will stop sharing.
Yeah.
Okay.
So this is like the homepage of our website. And we've added a small section for our syntax cheat sheet for our language. And this is the main online interpreter. So you can type programs in here, for example. Yeah. So here's an example of a small program that I've written to sort of show the addition operator. And this is string concatenation, as well as the runtime type checking. So let's run the program. So here's the output console, which shows that print2 plus 3 has printed 5 to the console. And hello world has printed hello world as well. But when we try to add a string to a number, we get a type error. Yeah. So here is a demonstration of how we sort of optimize tail recursive functions. So there are two different functions, but there are two different implementations of the factorial function here. The first implementation is the usual implementation, which is just recursive. And the second tail fact function is a tail recursive implementation of the factorial function. So for example, we can try printing out the result of fact 100,000. And when we try and do so, we get this too much recursion, which is just an output error message for when the stack exceeds its memory space. So then we'll try the tail recursive version, which prints out infinity as the result. Because the result of this factorial of 100,000 is too large to be displayed. And it doesn't seem very convincing. So we've also prepared another example, which is a summation from the numbers from 1 to n. So the first portion is a normal recursive function, and the second implementation is the tail recursive version of the above. So we can try what happens when we try and print the sum from 1 to
10 million.
Yeah, like we'll try 1 million. Yeah.
Okay.
So 1 to 1 million for the non-tail recursive implementation. So here we see that it explodes the stack. So it doesn't really work. Then for the tail recursive implementation, we can try it out, and we see that some output is generated. So we've optimized tail recursive functions to consume constant stack space instead of growing linearly for normal, like non-tail recursive implementations. Let's go back.
Oh, present.
Yeah, wait. So now I'll talk a little bit about the future direction of Solar. So we are planning on keeping the website alive by maintaining it. So we'll allow users which are interested to try out our online interpreter to go to our website and try it out. And developer documentation and our GitHub repository would be made public. So we are welcoming any feedback or contributions to our project. And I think that's all for our presentation today. So we're now open to questions.